Okay, this one is going to be on materials. And if you think about it, there's not a whole lot out there that you find in a factory. Ever since we stopped using rocks and pointy sticks, we don't use that many materials, different materials. We still do a little bit of wood. We're not going to cover that, hardwood flooring, furniture, that type of thing. But let's get into this. Now, there's a lot that goes into selecting a material for a product. You think about it, if I'm doing a electronic circuit, of course I want gold, right, as a designer. But man, it's expensive. Uh, and as a process design engineer, yeah, it's easy to work with. But you got to go back and forth, find the best thing. And it's all based on money, good enough to do the job. So it's a continuous process between the product design, the process to find out the right material. And the material kind of give you feedback too. We tried powdered metal once on a part, that sintered metal. Um, we thought we could get away with it, didn't do it, and tried it. The material said, hey, not me. So how do you select the material? Well, I want to emphasize this is a concurrent event, right? So it's not just the engineers, design process, everybody's involved, right? So first thing I do is what's this thing supposed to do, right? Then configuration, what's it going to look like? And then we do engineering analysis, the stress, strain, uh, that type of thing, right? Is it going to work? You choose your material, right? You first shot at it, say, okay, this is the right one for us, and then you optimize it. And this is where you go back and try it. You say, oh, I guess that plastic isn't the best thing for my cookie sheet. I might want to choose something else, right? So you optimize it. It goes back and forth. And again, this is where the material talks back to you. You set your tolerances, and not just dimensional tolerances, but also material tolerances. How many parts per million carbon in steel? How much plasticizer in the plastic? Well, how much color in the plastic? How thick does the composite layers have to be? All those things, right? Then after that, you choose the process that can do it. Again, if a Toyota will work, don't use a Cadillac kind of thing, right? And then the cycle starts. Then you come back and you redo the design, and you go through this all again. It just keeps on going, going, and going. And the big thing now is what do you do with it when it reaches this end of life? Um, there's a big problem with e-waste right now. How do you get the metal off that piece of plastic without just pouring tons of soot in the air? Um, Christmas wire, of all things, uh, Chinese are buying the scrap Christmas wire because they got a process now where they can strip the rubber off and recover the copper. So you got to think about that. That's a big one nowadays. Okay, let's talk a bit about metals. This is the big one. Used to be when the first metals came from. Basically, they just found pieces of metal like floating copper, a gold nugget. Man, if you found a meteorite that was made out of iron, that was a great find. But generally, you have to pull this out of some kind of ore. And there's different ways of doing it. There's pyrometallurgy. That's where you just kind of heat up the rock, put a little carbon in there, coke um, from fuel, something like that, and the carbon will basically get that metal out of there. Direct reduction, basically just crush the crap out of the ore, turn it into a powder, and then you take the metal out. Hydrometallurgy, that's basically if you got the right kind of ore, you can leach out the metal. You just put it in acid and let it dissolve and see what comes out. Electrolysis, and I'm good, but back when I was a kid, this wasn't with metal, but we used to go to the sand dunes in Michigan, along Lake Michigan, and we looked for lightning strikes. And where the lightning struck, it hit the sand and turned it into glass. Um, that's what electrolysis does. Basically, you send current through a rock, and then it melts. It just melts, and you pull it out that way. Pyrometallurgy, that's what you're going to see mostly in Mississippi County. Okay, this is a steel mill, and this is making iron from ore. The factories in Mississippi County use scrap metal generally. But so I'm going to talk a bit so you have a chance to watch this thing in action. Where did iron ore come from? Well, about 2.5 billion years ago, and I don't know if I can say this right, but it's called the Paleoproterozoic era. There's no oxygen in the atmosphere. So what happens? iron's just floating around in the ocean. Nothing's happening to it. And all of a sudden, plants learn how to do photosynthesis, started kicking oxygen into the atmosphere. The oxygen goes out in the oceans and oxidizes the iron. The iron precipitates off as rust and then falls to the bottom of the ocean. And it sits there again for 2.5 billion years ago. We come along, pull it out, heat it up, and make iron out of it. Now, if you look at this process here, right, we take that old iron and things like that, and we take it and we heat it up. And you basically melt the iron ore, right? Make like a slag out of it and molten iron. And then you put it in different furnaces. You pull it out. You got the arc furnace where you can temper it and get the treatment you want if you want to make steel or something. You melt it, and then you just cast this thing. It's a continuous cast. And if you get a job at a mill, you'll see one of these things. It's really fascinating to watch. The other thing you can do with it is you got extra iron. You can heat it up, add some limestone to limestone mixed with the impurities, come out as slag. Have you ever seen lava rock like in flower beds or something? It's old iron ore slag or steel mill or iron mill slag. Just pour it up into ignits, and those are pig iron. It gets its name because they look like little pigs. But this is how you make steel from iron ore. A lot of energy right here, a lot of energy. Ceramics, what are ceramics? This is another material. Well, it's inorganic, meaning it doesn't have any carbon. It's got very low density, and this is means it's kind of light. And you think about a brick, how heavy a brick is. Well, compared to a piece of iron or something, that's really not that heavy. In fact, some of these ceramics, you can actually get them to float. High temperature, you look at the bottom of like a spacecraft, it's all covered with ceramics because it's got to go up to 10,000 degrees Fahrenheit. So these things can take it, right? You got the traditional materials. This is stuff like clay. Think of porcelain, right? What that is, that's just clay that's cooked until it turns into porcelain, and it changes it's called vitrification, but it just changes the material on that, the characteristics. And of course, engineers are going to fool around with it, and they're going to make this advanced structural clay, and we can get different characteristics out of the ceramics: better, stronger, faster. And glass. Glass is a form of ceramics. So this is a chart of the different mechanical properties of ceramics. In other words, how strong they are, basically, is what we're looking for, or how much they give, bend without breaking. And I'll include one of these in the portal. So some interesting ones here. There's cubic zirconium. If you look at that, look how strong that is, right? And that's why you see it in rings in place of diamonds. It's hard, it'll last a long time. And you can actually, you got some glass in here that fused silica as glass. Soda lime glass is obviously glass. But you can get different characteristics on this. It depends on what you need. And KSI is a measure of strength. And modular elasticity, we won't get into that, but it's another measure of strength. Let's talk a bit about plastics. Well, plastics are made out of polymers, and polymers are just long chains of molecules with repeating similar types of atoms and molecules strung together. And plastics, it just has to be a carbon polymer. It's got low density. We've all know that plastic's very light. It melts, low temperature tolerance, and it contains different things. It can have fillers, stabilizers, keep it from breaking down, plasticizers, colorants, and different things. If you ever get a bottle, like a bottle of water, and you blend it and flex it, that's got what's called BPH in it. You leave it out in the sun, that will leach out, right? It's actually not good for you. It actually causes what's called endocrine interrupters. But they'll put all kinds of things in here, and eventually they come out. Very hard to break down plastic, these polymers. Very hard once you get to the bottom of that, the core of that, the essence of the plastic. Very hard to get that out. Of course, we got engineered plastics, right? And right now the industry is bigger than the metal industry. Almost all the Well, I say that. Uh, Big chunk of the factories work only with the plastics. And again, there's different types of plastics, and this is a chart of the various properties of various plastics. And there'll be some questions on the worksheet with this, so I'm not going to cover it much. And I don't know why Ken Yousefi highlighted nylon reinforced and polycarbonate reinforced, but he did it. There's no special reason for our class. And the last material we're going to talk about is composite structures. These are fairly recent. You think composites, it's just things like Kevlar, things like that. Fiberglass could be one if you do it right. Basically, it's just totally man-made, and we all know what that looks like. Bulletproof vests are made out of composites. A lot of armor is made out of composites, and other things that you need like hardcore strength on it, very strong. You can use these as surface treatment too. Right now there's a lot of interest in a thing called graphene, and your pencil has some graphene in it. Your pencil lead has some graphene in it, but it's very hard right now to get it out and make it workable. But basically do these surface treatments, and what it does, it adds a layer of protection to that surface for whatever reason. Semiconductors are actually composite. You got the N and P type material, and it's basically a semiconductor. That's how you make a semiconductor out of composites. And you join these things, you can snap them together physically, but usually they're just glued together in different layers. So basically these things usually come in sheets. And so you got to join them and make them somehow into a material that you can use. And you notice I don't have a chart for composites. The one you're going to be most familiar with is semiconductors. And you're going to learn about that in electricity. So I'm not going to cover it here, but just be aware that it's out there. So let's think about this stuff. All this material, we got to consider the environmental aspects, both in design. How do we minimize the environmental impact? And during manufacture, how do we minimize that? In about 20, 30 years, there's going to be more plastic floating around in the oceans than there is plankton. But it's going to be about the same size at micro level. And here's the bad part: is they found out that zooplankton, stuff that eat the green stuff, they actually prefer the taste of plastic over the stuff they're supposed to eat. So it's going to be interesting times. My generation's kind of screwed it up for the younger generation, but let's see what happens. So what happens, right? Well, we get the raw material extraction. Again, a lot of energy, right? A lot of energy to pull that out of the ore. We process the material, right? So we send the ore off, we make pig iron, or we pound it up into powder, send it off to wherever it's going to be used. We make the product in packaging. Again, we include packaging here. A lot of waste material in packaging. So we got some more waste coming out. We ship it. There's some plastic pallets, things like. Again, we got more waste being generated, and plus the CO2 and the NOx coming out of the exhaust pipes during the shipping. Diesel, going back to shipping, even diesel ships, incredible amount of pollution coming out. Diesel ships, and they can use that low-grade unrefined diesel, so a lot of soot. And I won't get into it, but it's doing a lot of health damage to the people who live in port cities. During the use of the product, of course, you generate some waste. Then you're done with it. What do? Well, we tend to just toss it in the trash can, but more and more is getting into recycled. It's scary, actually, the amount of garbage out there. Plastic's going to be around for at least 4,000 years after we use it. So, again, this is something you got to consider. It's becoming more and more. In Europe, in fact, they do this assessment, and they can actually put a cost. How much is the cost of this environmental cost of your product? And you pay a tax on it. So it's very important. So let's talk about a bit about recycling. Metal, that's pretty straightforward. When you get the metal melting it itself, you can actually pull out some new scrap. This is stuff that comes directly from the factory that makes the metal. Segregated scrap, that's where if you take it to a factory, let's say they're working with brass, and they keep all the brass chips after they turn it somehow. That's segregated scrap. It's strictly brass. Let's say you send it to a factory and they mix the brass up with a little bit of aluminum, some steel. That's mixed scrap. And then the old scrap, that's the stuff we put in the recycling bin. The tin cans, the beer cans, all that type of stuff. Ceramics, glass is pretty easy, right? You just chop it up and remelt it. You got to get the paper and things off. In fact, I just saw where there's a great big sand shortage in the world to make cement. And they're actually grinding glass up and using that as mortar sand. And it's really kind of a neat process. Ceramics, that's kind of tough, right? All this is cooked clay. How do you recycle that? And there isn't really not a very good way yet. Plastic's primary, right? If you get a job at a plastic injection molding company or something like that, you're going to see a lot of flashing, a lot of scrap coming from the plastic, right, itself. Well, that gets tossed back into the next batch usually. Secondary, this is where you put our stuff. This stuff you can put in recycling bins, the water bottles, things like that. Tertiary, this is where you can actually break it down, tear it up, right? Break it down to the polymer level, those long molecules, and use it as feedstock. Basically, you're making new plastic. Take it down to the very basics and making new plastic out of it. And then the last is quaternary, which is you just basically burn it and use it instead of using gas or oil or coal or something. You just use plastic and burn it. Yeah, okay. And composites. This is left blank because I really don't know how they can do that, and nobody does really a good effective way.